let's work out to the standard algorithm for multiplication. When I do 15 times 3, what I'm really doing is just adding 15 to itself 3 times, or you could think of it that way at least. So you take 3 copies of the 15, and then this now becomes an addition problem where we just combine all of the 1s and make exchanges when we need to, and then combine all the 10s and make exchanges when we need to, and so on if you have higher place values. So here I have 10 1s. I'll exchange them for 1 10, and so I'm left with 4 10s and 5 1s, or 45. If we did 15 times 3 with our standard algorithm, we would see this exchange reflected when we do the carrying. So 5 times 3 is 15, and 1 times 3 is equal to 3, but this is really 10 times 3. So 10 times 3 is 30. So this would be 45. How we normally write this would be 15 times 3. So 5 times 3 is 15, and we carry the 1 up here, and then 1 times 3 is 3, and then plus that extra 1 would be 4. So this is how we do this in like a more space efficient way. But this tends to make a little bit more sense to people. If you sort of write this out, people will be like, yeah, this makes perfect sense to me. And if you ask someone to explain like what the 1 is doing up here, that makes a little bit less intuitive sense. But it's easy to see that these two things are computing the same thing. If I do 15 times 10, that's more or less the same sort of thing. Let's get rid of some of this stuff up here, so we can do this. So 15 times 10 is the same as we do 10 groups of 15. So let's do that. Here's 5 groups of 15, and then I'll just double that. Okay. So I have 10 groups of 15. And now, again, this is an addition problem now, and I just have to make exchanges anytime that I need to. And what do you notice? Well, you notice since I made 10 copies of these 10s, then this is just going to be a simple exchange where I exchange these 10 10s for 100. So let me go down here and just grab one of these hundreds, come back up here. So I'm going to exchange the 10s for 100, just like that. And now what can we do with these leftover singletons? Well, I started with 5 singletons, and then I took 10 copies of each of them, right? So 10 copies of each of these singletons. And so I can make an exchange like for each of these 5 groups of 10, right? And so I'm going to exchange that all for 5 groups of 10. Get this. Okay? And so I started with 110 and 5 1s, and I end up with 105 10s. So that's why we have 150 now, which is really why we're really just shifting the place values by doing this. So adding a 0 right here just shifts the place values of all the digits, which is really just saying that we're just making a bunch of exchanges for all of our place values. Okay. And then if we were to do 15 times 20, we could really just do 15 times 2, which is 30, and then multiply by 10 just by shifting the place value. So this is 30, and then I shift the place value by adding another 0. Okay. And then if I were to go one step further, let's do 15 times 23. 15 times 23 is really, you could think of this as 15 times 20 plus 15 times 3. Do this in the same way that we just talked about. and then do this in the same way we just talked about. So this would be 300, and then this would be 45, which makes 345 total. And if we were to look at how this is reflected when we do our standard algorithm, 15 times 3, we just talked about it's 45. You could write that out however you wanted. And then 15 times 2, or 15 times 20, that would be, so remember that this is actually 15 times 20 at this point, and so we're going to have to put a 0 there to account for that place value, or just omit the 0 and just put nothing right there. And then 15 times 2 would be 30, and so then you just add everything up and get 345. Okay. And again, like the whole carrying thing, like that's just going to represent all of those exchanges again. All right, let's look at division. 431 divided by 3. So much like subtraction, I'm not going to want to represent the number that I'm dividing by here. I'm going to try to only represent the number that I'm starting with, and then do something with that to reflect the 3 at the end. Okay, with subtraction, if I was like subtracting 3 or something like that, then I would just like end up with like the 3 that I subtracted just like off to the side, and then look at how many am I left over with. With division, what I want to do is split this into groups, or so you could actually think of this as like a how many groups approach, or how many in each group approach. Here I'm going to think of it like this. I'm going to say I have 431 blocks, and I want to divide them into 3 equal groups. Okay, and then I want to know how many is going to be in each group. So it's a how many in each group approach. So let's do that. So let's go biggest place value first, and then work our way down. So I'm going to try to split these into groups, into 3 equal groups. So I have, zoom out a little bit. So I'm trying to do 3 equal groups. So I have 4 100s. So I'm going to take 3 of them and divide them among the 3 equal groups that I'm trying to build. So I'll just kind of separate them off a little bit like this. This will be like group number 1, group number 2, and group number 3, and I'm going to make 3 equal groups. Each group's going to have the same number of things in each of them. Okay. Now this leftover 100, I have to do something with that. I have to do an exchange. So let's do an exchange. So let's do that. Exchange this 100 for 10 tens, so that now I can divide the 10 tens equally among the 3 groups. So how can I do that? Let's see. How many do I have right here? I have 13 tens. So if I'm dividing 13 tens among 3 equal groups, each group is going to get 4 of these 10s. Okay, and then I'll have 1 left over. And now I have to do another exchange. So I'm going to exchange this 10 for 10 ones. And I have this 1 left over. So now I have 11. I need to divide those among 3 equal groups. Okay, so think I can only do groups of 3 for that. So 3 in each. 3 in each group, and then I have 2 left over. So 431 divided by 3, what does that equal to? Well, so I have split them into 3 equal groups, and then each group has 100, 4 tens, and then 3 ones. So 100, 4 tens, and 3 ones left over, and then I have a remainder of 2 left over. Okay, so we now see that 431 divided by 3 is equal to 143 with a remainder of 2. And if I were to do this in the standard algorithm way, 431 divided by 3. This whole process is very much reflected in the standard algorithm. So, 4, I see how many times does the 3 go into 4? Well, once. And so 1 times 3 is 3. Take that away. Really, that's like 300. So this is representing, I have 100. That's why like this is above the 4, because this is for the hundreds place. So I have 100, and then times 3 is 300. Go away. Take that away. What am I left with? I'm left with 131. How many times does 3 go into 12? Goes in there 4 times. 4 times 3 is 12. Take that away. And also, since this is really like 4 tens, this is like 40. So 4 tens times 3 is 120. Take that away. I'm left with 11. And how many times does 3 go into 11? It goes in there 3 times. So 3 times 3 is 9. Take that away, and I'm left with 2. So I get 143 with a remainder of 2.